So as Matt introduced me, I will go ahead and get started. My name is Mike Benshoof. I am a technical account manager with Percona. And what we're going to talk about today is the MySQL schema review. So this is going to be kind of an intro level talk in terms of schema review, but it's actually something that's very important and has sometimes been lost with a lot of the migrations to the cloud and some of the typical DBA type tasks. We want to really switch our focus to looking into the actual schema and optimizing it. So this talk is going to really go through what we want to look at when we're reviewing our schema. We want to make sure that our schema is optimized. We're going to look at some different tools that we can go through and use to isolate issues that we're seeing in our schema and that are resulting in performance or other problems. And then we're also going to talk about what problems can be caused by this. Again, this is something that is frequently overlooked, especially with the big push to going to cloud and really not having to set up the actual database servers anymore. This is really something that we want to squeeze the most performance we can out of our instances, and a lot of times it comes down to the schema. So let's go into a high-level discussion of really what is a schema. So a schema essentially is the formal definition of how data is organized. So again, we hear a lot of SQL versus NoSQL, schema list designs and that type of thing. So we're really looking at a schema standard SQL relational database structure. And what the schema is a collection of tables, indexes, and functions. The schema itself is owned by the database instance, and permissions are then granted to the different tables and functions and views either at the schema or the table level. So this is where we can look at doing a grant select on the entire schema. We can do grant select on certain tables, inserts, and that type of approach. So we're going to go through and review just a sample schema that I put together. This is nothing fancy. This is just to kind of illustrate some of the things that we look for when we're discussing our schema review and different tables and how we want to make sure that we're fully optimized. And the main pieces that we're going to go through are going to be our data types and indexing, right? These are two pieces of schema design that are really important. Obviously, when you're designing a relational database, making sure that you have all the fields that you need is important, and making sure that you have the proper relations is there. And the way that we optimize that is through indexing. And then data types, right? What those actual fields are and the type of data that's stored there. It's actually very, very important that we follow through with that. So let's start with data types. When we look at data types, again, this is something that is often overlooked. People will just say, well, it needs to be a number, so I'm just going to make it an int, or do I use a small int? Do I use a big int? Choosing which type you want to use, really the main thing comes down to choose the smallest type that you can. And why this is important, the size of data type, again, when you look at an individual row, it's generally irrelevant or not really noticeable, but when we start to look at larger data sets and as your data grows, it becomes much more impactful in terms of disk space and also memory buffer allocation, right? When we do query operations and when we are executing queries, if things need to be put into temporary tables, as pages are loaded into the buffer pool, these are all impacted by the size of the data types that we choose. And each data type has a different size, right? So choosing the smallest one is going to be of the utmost importance. So let's take an example table. We looked at this action table, and in my setup, I took the same table and identical data, right? I created around 4 million rows, and it was just 4 columns with 3 indexes. And then I created a copy of the table, exactly the same, And the primary key on one table was a regular int, and the primary key on the other table was a big int, and just did a select into. And when we look at the outcome of this, you can see right here, we're talking over, 250 megs of space on a less than 1 gig table. So, we're talking a large overhead just by changing the type, right? Because a big int is going to be larger disk footprint than a standard int. So that's a lot of overhead when I have the exact same data in both tables. So again, this is why choosing that smallest type that you can becomes important. So when we talk about that, another thing that is often overlooked is signed versus unsigned integers. So a lot of times when we look at, especially using primary keys, we set an auto increment as our auto increment integer as our primary key, and we just are constantly increasing that, right? Our IDs are just a numeric increasing number. One thing that we want to look at here is when we're defining that primary key as an integer, we want to make sure that we use the unsigned type, especially when we're using an auto increment, because we're going to constantly be increasing. If we were to use a signed int, what that is going to do is going to change our range, and we're going to basically have 2.2 billion rows versus, 2.1 billion rows versus 4.2 billion rows. So, instead of having our range from negative 2.1 to positive 2.1, we're now looking at 0 to 4.2. So right there, that doubles the range that we can get, and we're not actually increasing the size of our data type, but we're just starting from 0 because we're never going to have negative primary keys because we're incrementing by 1 each time. So that's an important piece to look at. Another piece that I have seen a lot in various optimizations and discussions, using timestamp versus the date time types. So timestamp is going to be a smaller footprint, and it's going to be much more optimized for tracking when things are touched, right? If I'm going to mark a record for when there's an update made, that's going to be a great use case for using the timestamp. If we're looking at historical dates, people's birthdays, assuming all of our users are not born after 1970, we're going to need to use date time, but we definitely don't want to use date time if we're doing all of our updates and historical tracking, because again, we're talking about the size, and we want to use the smallest that we can, and a timestamp is optimized in a smaller footprint. So we've gone through the data types. As we talked about at the beginning, we also wanted to go through indexing and kind of how indexing works and how we want to create our indexes and optimize those at the schema level. So from a high level, indexing really is just meant to speed up data retrieval, and it works the same way that you would with a normal book and that index. I can look for a specific word and find that page. It'll point me to that page and I can find it. Secondary indexing is the same concept. If I have my primary key is set up as a user ID and I have an index on their last name, just like I would go for looking at that name reference in the back of a phone book, I'm going to look up that name and I can jump right to that, and then that'll point me to that page, as opposed to having to go through all the records and sort through them one at a time and check for matches. So when we look at indexing, the key principle that we want to focus on is using the fewest possible indexes that we need to ensure optimal performance, but making sure that we are indexing things that need to be indexed, right? So again, we don't want to over-index and we don't want to under-index. This is kind of a piece that is a continual review. You want to make sure that things are, you're not being hit with performance because you're missing indexes, but you also don't want to have a whole bunch of indexes that you're not using. And why does this matter? Because indexes, again, are needed for the optimal query execution. So again, I just gave that reference. If I have a user table and that user table is all with primary keys of a user ID, and then it has their names, and I say I want to find the user with the last name Benshoof, well, when I have to go through, if I don't have an index on that last name, I'm going to have to go through every single row and check the last name column. So we definitely don't want to do that. That's called a table scan, and those are definitely operations that you want to try to avoid. So that's why we want to make sure that we have indexes there for the proper query execution. However, when we look at not over-indexing, indexes do have an additional cost, right? So to have an index, we have a space penalty. So we're going to be using disk and memory for this. And we also have a write performance hit because we have to maintain these indexes. If I insert a row in the middle of a table, not only do I have to update the table space and the main source of records, but I'm also going to have to update that secondary index based on those fields that I'm indexing. So some extra things to consider when we look at indexing. When using InnoDB, the primary key is appended to the end of secondary indexes, right? So this is done as a performance optimization that when I find a page in my secondary index, I can quickly have reference to the primary key and find that data. So why that's important is if our primary key is large, that's now being appended to all of my secondary indexes. So the penalty that we're going to see from a larger primary key is duplicated because I have multiple secondary indexes and I keep reintroducing that performance penalty and that size penalty. The other piece is that when we look at indexes, composite indexes, they move from left to right, right? And that's how we would read that. So if I have a secondary index that has 3 fields, I'm going to work my way and check the first field and then the second field and the third field. If my query only has the first and second field, it can use it. However, if my query only has the third field, it will skip that secondary index. So we want to look at that in terms of how we're writing our indexes, but we also want to be mindful of that to prevent duplicate indexes. And knowing our query traffic is really going to help here because we can combine those queries based on, or we can combine those columns based on the queries that we know are coming in. So when we know that we're going to index or we're going to query on 1 or 2 of these columns, but this is always the column that's going to be included, and we may add the second one, that would tell us that the column that's always going to be included is going to be our leftmost column in the index, and the column that may be added to the query would be our second column in the index. And along with that, when we look at which columns and which order that we want to use with composite indexes, we want the most selective columns on the left, right? So if, for example, if I have a table that has, 1 million rows and it has 1 million unique user IDs, and they have a status of active or inactive, and 95% are active, if I were to put an index on that non-selective row, it's really not going to help me isolate things very much, right? Because the majority of the time, I'm going to be covering the majority of my rows anyway. So I'm not really using the index to find anything that is going to be shorter, right? For example, let's use that phone book example again, and everyone in the phone book has the same area code, but they all have different last names. If I look up by area code, I'm still going to have to read through everyone, right? So that's where the last name is going to be a much more selective piece. So that would be the column that I would want first in my composite index. And finally, when we're reviewing our queries and we're reviewing this traffic, we want to make sure that we use explain to verify which indexes are used. We may write an index that we think is perfect, and then when we run the explain, we see that that index isn't actually being used, right? So that's where we want to review that and make sure that it is actually being used. So some tools that we can use to profile schema. So a very quick overview, PT MySQL Summary, is a tool that can quickly review a specific schema. So for this example, I ran the tool, gave it the database tech days, which is where I have my sample schema. It highlights the number of tables, and if you look towards the bottom there, one of the key parts is that we have a breakdown of the different data type columns, right? So this is the aggregate across the database of what the columns are. And this is where we can start to see, do we have a lot of big ints? Do we have a lot of date times? We can see some of those things right off the bat as red flags. The information schema is another key source of information. We have the breakdown of our tables within there. We have information on the actual tables, the indexes, estimates on sizes, the cardinality, all of these pieces that I've just discussed. We can get that information breakdown from the information schema tables. One thing to note, the stats on metadata is a variable that you'll want to be aware of here. If we have that set to on, as I'm querying the information schema tables and indexes tables, what that's going to be doing is recalculating my statistics. So keeping an eye on that, that can add some impact to the server. So we want to make sure that we're not always doing that. So if you're going to be doing a lot of profiling of the schema, turning that off would be helpful. So here's a quick query that we can use to find what our largest schemas are. So in some cases, if I have a multi-tenant database, right, and I have 10 or 15 different schemas on here, and I want to find out which one is the biggest offender, this will group my tables and the table size based on the actual schema. So let's do a sample here. So right here we can see I only have 3 databases here. Again, this query isn't as useful if you're using a single schema on the instance, or this is the one, my primary schema. But if you have a lot and you're trying to isolate which one is the largest and causing the most pain, this is a good way to find that. So here we see the tech days schema, the one that we're looking to optimize, and some general information. There's the aggregate row estimates and data and all of that. So now what's a lot more interesting than that is when we look at the largest tables, right? We're trying to find the actual biggest tables that we can optimize. So if we modify this query a little bit and we start grouping it more by the actual table name, we can actually see here's our individual tables. And again, this is a full breakdown within that schema of the tables sorted by their size. So I'm working my way down from the largest tables. In this case, we can see that the action table is my largest with just under 4 million rows. Again, these are all estimates. They're not exact, but they can give you a good idea of where to look. So going through that, just kind of going through what is in that, that previous table, engine, table name, those are exactly what you think. It's the engine that you're using in the table name. The rows is the estimate number of rows over the table. The data index and IDX and total size, those are estimates of the actual data and index sizes on disk. So remember, we've got our main data, and then we have our secondary indexes. So this is showing us how much of our space is within the table allocated towards the actual data in the primary index, and then all of our secondary indexes. And this last column is one that we calculate, and it is the index fraction. And basically what this is the ratio of the index size compared to the data. And so we want to make this ideally less than 1, and we want to keep it smaller. The smaller this number, the less overhead we have in terms of disk space for our indexes. Because again, this is the ratio. This is comparing our actual index size to our data size. If we see this number over 1, that means that our indexes are actually larger than our raw data. So if we wanted to modify the previous query, instead of saying, let's sort by the largest table, we can sort by this ratio, and that will basically target the tables that are the most skewed, which have the indexes larger. Sometimes this is helpful, sometimes it really depends on your particular schema. So again, what can we learn from this? The IDX frac column, a lot of times this means we've used the wrong choice for a primary key data type, and then we also have, or we could have a large excess of indexes. The rows and size, those can give us tables that we want to focus on for archiving, retention, and partitioning. Again, one thing that we talk about in performance, querying less data is always going to be faster. So knowing which tables are your largest and getting that data out of the database can make that process a lot easier. So duplicate keys, this is something I mentioned. You can use information schema to find this, and looking at those columns, that gives us an idea of where we might have some duplicate indexes. But there is a tool from Percona Toolkit called PT Duplicate Key Checker, and that can quickly identify those problem indexes and actually give us the alter statements to remove them. So running this against our schema, we find that I have a duplicate index here on the action table. And when we look at this, what we're seeing is we have two columns, one with the user ID and then one with the user ID and created at. And again, this tool will give us what the problem is, and I've duplicated leftmost prefixes. So if I use a query with user ID, I can use the one that's composite because it's the leftmost. So it will give me the alter statement to drop that index, and it'll give me also a summary of all the number of duplicate indexes and the size overhead that I'm seeing from that. So that's a great tool to quickly identify those. Unused index is another piece, right? Sometimes as developers come in, they just index every column thinking, well, I'm going to have all these queries and we're going to put, every index because I don't want to get in a situation where I'm doing table scans. And as your database runs for some time, you start to notice that some of those aren't actually getting touched. So finding those unused indexes to drop, they're not necessarily duplicate, they are used, but if your database your server's been up for a month and your table, you're running thousands of queries per second and this index has never been touched, odds are that it's not necessarily needed, and that's something that could be a target for removal. So the user stat module or performance schema are two different options that we can use to isolate these unused indexes. So what we did, I basically restarted and flushed everything and then ran a few queries that would just be standard queries that we want to look at. And now this is using the user stat module. If I look at the index statistics table, this shows me all of the actual index rows that were read, right? So this shows me that I used a couple of secondary indexes and a few primary indexes. But now, the point of this was to find indexes that are not being used. So if we combine this with our actual base index statistics that have all of the indexes, and then we combine that with the indexes that are actually being read, we can get a quick list of all of the indexes that are not being read. So this is one approach that we could use to find indexes that are not being touched using the user stats module. Performance schema has another approach and a view that comes with it, and this one is probably much easier. So as long as their performance schema is already on, which theoretically you can keep that on, or it probably is on in your environment, you can just quickly use this and get an even faster snapshot of the indexes that have not been used. And again, those can be, you could do code reviews or other things, take a deeper dive to make sure those aren't actually needed. So again, let's go through, and I'm going to make some changes to my initial table that wasn't in the best shape. And we're going to use some revisions based on this and see what we can actually gain from it. So the first step, I had that duplicate index that we saw, remember, from PT Duplicate Key Checker. So I simply dropped that index, and right there, dropped almost 200 megs off of my table. So a really noticeable and immediate impact was seen by dropping that. Data types, this is another piece that we did. So we saw that the event and the user event table had those high IDX fracs, right? So they were larger indexes than data. So when we go back and look, in these cases, I had used a character field for my event ID, right? So this is maybe a UUID or something like that that's been generated. So not an uncommon approach. So when we look at that, I reference this, I have the primary key, I have multiple secondary indexes. I remember we talked, the primary key is appended. So each time I'm doing this, I'm adding this primary key and this 36 character string to the end of all of my other secondary indexes. So let's make two new tables and kind of transition this and just see how it looks. So I want to just show the impact of something as simple as an increment, an integer versus a character primary key. So here we've changed this, and now I have an unsigned auto increment, and I'm using that for both of my tables. I'm taking everything from my event table, so this is just to show that I'm using my existing data, and all I'm doing is changing the primary key type. And then I'm dropping the old character keys at the end. And let's look at the impact right here. So just with that alone and those two tables, that saved us over 50% reduction in space. Again, this is a small scale table, and we're talking, you know, on the order of megs, but still it's something to note that when this gets expanded out and as your database grows, this is a very noticeable improvement. So now when we look back at our breakdown, you know, we can look right here. See, beforehand, the event table, the data was larger, and we dropped that ratio from 1.12 all the way down to 0.38. So much better approach right there. So not only did we shrink the table by changing the primary key type, that also then reduced the secondary indexes that came along with it. And now I have a much leaner table that's easy to access. So again, just kind of in review, some of the main impacts that we see from schema optimization or not having your schema optimized is wasted resources, the individual session buffers, the buffer pool itself, and then disk. Suboptimal performance, right? When we have to update 10 different indexes, that's going to potentially slow our write performance. So having suboptimal performance is another thing to look at. And also it's additional overhead for the optimizer. If I have to analyze 12 different paths instead of 3, that's an extra step that needs to be done. And there's a better likelihood that I can choose the wrong path, which is going to be an impactful thing that we don't want to do. And just kind of to wrap things up, this is not a one-time approach, right? This is an iterative process. As code changes, especially with more agile development cycles, things are changing. We need to continually review this. We need to look at our tables growing over time. We need to continue to review indexes. Are they being used? Are they not? By watching this over time, again, we can understand questions like, when are we going to need more disk space? How frequently do we need to archive? Are we missing indexes? And these types of questions. So I think that is my time. I don't know if we have any time for any other questions or if any have come in, but just another reminder, we do have Percona Live Online coming up the 20th and 21st of October. So hope to see you there, and we can see what hats Matt will break out for that.